Hi, I'm Brian Mullen, and this is Balls Out Physics, episode 1.2, Flying Over the North Pole. I gotta thank Deep Inside the Rabbit Hole for pointing this out, because it really helped me develop a south-north-north-south flight problem, where I think the issue that I was trying to explain in episode 1.0 is really shown. And so, what I have here is a view of the Earth looking down on the North Pole, kind of like I was talking about in episode 1.1, looking down on the North Pole like this. What I have is Quito, Ecuador here, and Singapore over here. And so, if you look at this on the globe right here, Quito is right here in Ecuador. We're going to say it's right at the equator. It's a little south. Okay. We're going to take a flight from Quito over the North Pole to Singapore over here by my thumb. Okay. Now, Singapore is at 104 degrees east of the prime meridian, and Quito is about 78 degrees west. And so that's 182 degrees between them. But I'm showing a straight line here. We're just going to assume that they're 180 degrees away from each other. And the runway at Quito actually faces almost due north. So we can say that the pilot's going to start off and fly directly at the North Pole. Okay? And so when a plane is sitting on the runway, it's moving with the Earth, right? If in the heliocentric model, if the Earth is rotating about its axis, we're all moving. I'm moving, you're moving, we're all moving at different speeds based on how far we are from the equator. Well, that's the way I figure it out, at least. And so at the equator, I'm going to say here that the circumference is 25,000 miles. You can say it's a little bit less, but we're just going to keep it simple and say 25,000 miles. And we're going to say that the Earth makes one rotation in 24 hours. Now, you could argue that in the heliocentric model, the Earth makes one complete rotation in a sidereal day, which is 23 hours and 96 minutes, but that's a topic for another time, and it's only 4 minutes difference. And we're also going to say, to keep things simple, that the flight from Quito to Singapore takes 24 hours. And we're also going to say that that distance is 1/2 of the circumference of the sphere. We're assuming a perfect sphere here. And so that's 12,500 miles. And if it takes 24 hours, that gives you an average flight speed of 521 miles per hour, which is very possible. And flying 24 hours is also very possible. I looked it up, so the longest flight ever was for 4 days. They're probably refueled in the air. But a plane could be outfitted to fly from Quito to Singapore. So now, when the plane is sitting on the runway in Quito, facing north, here on Quito, the Earth is rotating, right? And so, if the Earth makes one rotation in 24 hours, 25,000 miles circumference divided by 24 hours gives you speed and instantaneous velocity on the Earth of 1,042 at the equator. At the equator gives you an instantaneous velocity of 1,042 miles per hour. Now you notice for the plane, I wrote speed instead of velocity, because in physics, speed is just a rate, whereas velocity is a rate and a direction, or having a vector. And I'll get back to that in a minute why I wrote speed there. So the plane is sitting in Quito, use a marker here to represent the plane, facing due north towards the North Pole, and it takes off and leaves the runway. And as the plane begins to fly towards the North Pole, well, the speed of the Earth below the plane would change, right? Because since velocity is distance divided by time, or speed is distance divided by time, whatever you want to look at it, the circumference of the Earth around the axis of rotation decreases as you fly north, right? Because the Earth is curved. And so I just did this by drawing in CAD. When the plane gets to New York City, or at the same latitude as New York City, around there, the speed of the Earth has dropped to 800 miles per hour. But the plane should still be moving at VE, the velocity at the equator, with 1,042 miles per hour, right? Because on the runway, it was moving 1,042 miles per hour. What slowed it down? That's its moving. If you go back to episode 1.1, I was asking the question, how does the atmosphere spin perfectly with the Earth? Let's say it does. If that's true, does it create a suction force on the plane to slow it down? How does the plane match the speed of the Earth? How would it stay in a straight line? Would the pilot have to be constantly turning to the left a little bit to stay pointed at the North Pole, since the Earth is slowing down under it? And you see, when you get up here to 68.5 degrees north, the speed actually reduces to 400 miles per hour. How would this work? And I mean, this just isn't in this theoretical problem here. Anytime a plane is flying south or north, this problem would exist. That's whatever speed they started out on the runway, they would still have in the air. Now, if they're flying east-west, you could argue that the atmosphere slows the plane down, or as necessary, as was the response to my first video. But in this case, the plane takes off and the Earth is slowing down below it. I think it would actually go like this, maybe, or the pilot would have to keep adjusting. And of course, there's also what I mentioned in episode 1.0 of the plane having to constantly nose down to follow the curvature of the Earth. Now, the explanation for that was that gravity does that. Okay, gravity takes care of that, so the pilot doesn't have to do that. Okay, so if we were going to look at the Earth this way, at this flight, say we're going to look at it in this direction as it's flying over the North Pole,